Alright, so like we said in class, the first derivative test for where the function is increasing and decreasing says that whenever the slope, or the derivative, is greater than 0, that means it's positive, at each point from a to b, then f is increasing on that interval. And if the slope, or the derivative, is negative, less than 0, it is decreasing on that interval. So we're going to do the cut point sign chart method for determining increasing and decreasing, and these are the steps. So determine the critical points first, like we've always done, which is find the derivative, see where it equals 0 or where it's undefined. We're going to divide the x-axes according to these points, and then we're going to calculate the sign of the derivative on each interval. So we want to see, is the derivative positive or negative in between that interval? And the way we do that is we plug in the critical point to the derivative to see if it's positive or negative. Remember, it's different than what we did in section 1 because before we were plugging in the critical points to the original function because we actually wanted the y value of the original function. Right now we're going to plug it into the derivative because we want to know, is the derivative positive or is the derivative negative? So in first hour, I know we completed this example in class, but in second hour we did not get to it. So I'm going to show you guys how to do this. So we are going to determine the intervals. So that means at the end we're going to write an interval notation on which this function is increasing and decreasing. So step 1, we got to find the derivative. The derivative of 1/3 x cubed minus 3x squared plus 8x is x squared minus 6x plus 8. Now, in order to find where the derivative is 0, right, we're going to factor, and we're going to use the zero product property, and then these two are my critical points. So that was step 1, was determining the critical points. Step 2, we want to divide the x-axes according to these points, and basically just draw a number line and put those points on the x-axes. Now you remember from last section that these points represent the max and the min, right? So this is the absolute max and this is the absolute min. Now of course we weren't given an interval, so there could be other local maxes and mins, but these are the ones that we're going to worry about because the interval is all the full domain. So I put those two right here because I know at this point what is going to be the derivative. The derivative here is going to be 0 and the derivative here is going to be 0. The question is what's happening before that 0, after that 0, before this 0, and after this 0. So what we did is we picked a number. So in this case we picked 0. We plugged it back in to the derivative because I want to see what the derivative is. So we plugged it back into the derivative right here. And we end up with, when you plug in 0, so it's 0 minus 0 plus 8, that's positive. We picked 3, a number in between these two. We plugged it in, we got 9 minus 18 is negative 9 plus 8. We got negative. And then we picked a number here, let's say 5. We plugged it in, 5 squared is 25, minus 30, which is negative 5 plus 8, we get positive. So now I know that my graph is increasing all the way from negative infinity to 2. And then it's also increasing from 4 to positive infinity. And it's decreasing from 2 to 4. So my graph kind of looks like this. Now the question is, we don't know right now what these points are, but we can figure them out, right? All I have to do is plug in f of 2, f of the critical point back into the original function, and plug in f of 4 back into the original function, and I will get my y values. But that was from section 4.1. Alright, next problem. We're going to do the same exact thing, but the algebra behind this problem is just a little bit hard because the way that we're finding the derivative. It's not harder, it's just, cleaning it up is a little bit ugly. So right off the bat, you notice that these two things are multiplied. So in order to figure out if something's increasing and decreasing, step 1 says determine the critical points. And how do we do that? We have to find the derivative of x. Now the derivative of this is going to be using the product rule. So when you use the product rule, it's the first guy, right? So x to the 2/3 times the derivative of the second guy, which is 1. I'm not going to write it down because anything times 1 is itself. Plus the derivative, the second guy times the derivative of this first guy. And the derivative of x to the 2/3 is going to be 2/3 x to the negative 1/3. Now before I can figure out the zeros, I need to simplify this a little bit. So here's the process for simplifying. So first off, I'm going to multiply these. So I end up with 2 times x plus 5 over 3, and because this is a negative, I'm going to bring it down to the bottom, and I'm going to call it x to the 1/3. I don't know why I put a plus sign here. And then this is x to the 2/3. Okay, so that just comes down. The next step is I want to get a common denominator because I still can't figure out where this is 0 right now. So if I get a common denominator, then maybe I can combine them and end up with just a division problem. So to get a common denominator, I'm going to multiply the top and bottom of this by 3x to the 3rd. And then what we end up over here is 3x to the 3rd times x to the 3rd. Do you remember what you do when you multiply exponents? You add them, and that actually cleans up to be just 3x plus 2 times x plus 5, and now we have a common denominator of 3x to the 3rd. So I'm going to continue cleaning this top part up. So 3x plus 2x plus 10 over 3x to the 3rd. And the final stage, combine these guys. So 5x plus 10 over 3 cube root of x. Okay? And now we can find the critical points. So now I can set this guy equal to 0 and kind of find my critical points. So for this to be 0, that means this top portion has to be 0. So when will 5x plus 10 equal 0? When x is 1/2. So that's one critical point. Another critical point is going to be the denominator. If the denominator is 0, then what happens to this whole entire function? It becomes undefined. So when will the denominator be 0? If x equals 0. So these are my critical points. Oh, and this should be negative 1/2, sorry, because you're subtracting 10 and then dividing by 5. So step 2, I'm going to put these on my axes, and negative 1/2 is going to go first because it has to go in order. 0 is going to go second. And now I'm going to plug these points, or points in between these critical points, back into the derivative. So if I plugged in what's less than negative 1/2, negative 1, if I plugged in negative 1, I'm going to end up with, oh, and this is supposed to be cube root, so sorry, cube root of x, because if it was square root, then you can't, that's all undefined. But if I plugged in negative 1 into this problem, so 5 times negative 1 plus 10, 3 times the cube root of negative 1, which is negative 1, I end up with a negative answer. If I plugged in a number here that's in between negative 1/2 and 0, so we can plug in negative 1/3, negative 1/5, whatever you want to do. If you plug in negative 1/5, you'll kind of end up with a positive number up top and a negative number on the bottom. so a negative and a negative, so you end up with a positive answer. And then, I think I'm mistaken here. Let's see. That's negative 1 plus 10 is 9. And 3 times the cube root of negative 1/5, which is negative. So this actually should be a negative. I don't have my calculator next to me, but you guys can check it out and let me know if I'm right or wrong. Okay, if I plugged in a number in between this interval. And then if you plug in a number over here after 0, you end up with a positive. So if I plugged in 3, 5 times 3 is 15 plus 10, that's going to be positive over a positive, and that's going to be positive. So now my increasing intervals is from 0 to infinity, and my decreasing interval is from negative infinity all the way to 0. Okay, and then you can graph this function to kind of, double check yourself, but it should be decreasing, and then at this point you're going to end up with a 0 slope of some kind. It's going to continue decreasing. At this point you're going to have an undefined something, so it could be an asymptote or it could be a cusp or a corner, and then it's going to increase. Okay, moving on. We're going to sketch the graph of a differentiable function through the points 2, 3. So the point is going through 2, 3. It's differentiable, which means that it's continuous. And there isn't any cusps, corners, or asymptotes. They tell us that the derivative at 2 is 0. So basically what you're doing is you are drawing the graph. The graph is going through 2, 3. So at 1, 2, 1, 2, 3, there is a point, and it's going through that point, and what this is telling us is that at f of 2, the slope is 0, which means that that could be a max or a min, but we don't know yet, right? This next part says whenever x is less than 2, so for all of these points on this side, the slope is positive, which means the graph is increasing to this point. And then at this point it's 0, and then when x is greater than 2, so everything after here, the slope is negative. And that's it. That's all the information they give us. So this is y equals f of x based on this information. Next example, it says it's the same, except the derivative of f of x is greater than 0 and x does not equal 2. So everything's the same, which means that f of 2 is still 3, and that the slope at 2 is still 0. But what this is telling us is that x does not equal 2, so x does not equal 2. So that means we're going to have an open circle at that point right there. So we're going to change the fact that the derivative of f of x is always positive. Okay? There is a point at 2, 3. And the slope at 2 is going to be 0. It's just not at 2, 3. Now, this didn't make a lot of sense to me in the example just because it says same as 3 except this and this. But for it to be same as 3, that means these two are in play. So what I figured is that there is a point at 2, 3. The slope at 2 is going to be 0, except here the slope is positive, this is 0, and then it continues on to be positive. Because it's positive, positive, but the slope here is 0, except that it's not at the point that was given. That's how I read it. So we'll keep it like that. All right. Antiderivatives is exactly what it says. It's basically going backwards. All right. A function, big F of x, is an antiderivative of little f of x if the derivative of big F is equal to the function of little f. Okay? And for this happens for all x in the domain of f. The process of antiderivatives is also called antidifferentiation. Just like when you say find the derivative, it says differentiate. So we're going to stick with the easy problems when it comes to this. So let's find all possible functions with the derivative. Now keep in mind, just a little side note, there is a corollary that kind of goes with this. Alright, so if I was to ask you, I'm going to do a little side example. What is the derivative of y equals 2x plus 4, and what is the derivative of y equals 2x plus 144? What's the derivative of this? It's 2, right? And what's the derivative of this? It's 2, correct? So basically, what the corollary is it says that if they tell you the derivative is 2 and you want to find the antiderivative, you know that one of them is going to be 2x because you're working backwards. The question is you will never know what this constant is, and if there is one. It could be 0, it could be 1, it could be -1, it could be whatever. So, what the corollary says is when you're finding the antiderivative, the function is always going to be the antiderivative, which is going back to the function, plus some constant c. So the way that we do this is we literally just always write plus c. And I'll show you what I mean in just a sec. So here, finding the antiderivative of the derivative 2. So the only way that you can get 2 is if the function was 2x, and then we're going to add c. Because we could have gotten 2 if this was 0, 10, 20, 40, 400, it doesn't really matter. Okay? And you can check yourself by saying, okay, what is the derivative of this? The derivative of 2x is 2, I'm good. So that's finding the antiderivative, you're just working backwards. Part B. So what is the antiderivative of sine of x? So we know that the derivative of cosine of x is negative sine of x, right? But we ended up with a derivative of just sine. So that means the antiderivative is not going to be cosine, but it's going to be negative cosine. So f of x is negative cosine of x plus c. Okay, don't forget that plus c, and then you can check yourself. So what is the derivative of negative cosine of x? Alright, well the derivative of cosine of x is negative sine of x times another negative is sine of x. So we're going to stick with the easy problems for finding the antiderivatives, but it is very important that you get them correct. okay? All right, number 2 is using antiderivatives to kind of work backwards, okay? So here, with what velocity will you hit the water if you step off a 10-meter diving platform? And with what velocity will you hit the water if you dive off the platform with an upward velocity of 2 meters per second? Okay, I'm going to give you guys a little hint. We know that gravity, or acceleration, when you are diving is 9.8 meters per second squared, correct? And we want to figure out velocity. And if you remember, velocity is the first derivative and acceleration was our second derivative. So to find velocity, we need to go up and find the antiderivative of acceleration. Now I'm going to stop here. I'll let you guys kind of play around with this. We will go over it in class just because it does need a little bit more explanation, and I'm already at 21 minutes. Okay, enjoy.